All right, we need to look at the solution to the Schrodinger equation. By the way, this is quantum mechanics, but the old name for quantum mechanics was wave mechanics. So this truly is the math behind waves. And it's simply stating here that if you have a wave that exists as a stationary, standing wave or in a stationary state, meaning that it's got these fixed ends, or it doesn't matter if it's in a straight line, or if it is this wave that exists around the nucleus. I know I can't draw. What we are going to have is it's going to be quantized, meaning it exists in only certain energies. We could look at this as a mathematical equation, but we're not. We're going to do a simple address system. And this address system is going to use 4 quantum numbers. And in some ways, it's like a street number followed by a street name, followed by a city, followed by a country. It's just kind of a big picture going down to the details on where we can find this electron. So our solution to the Schrodinger wave equation is going to depend on 4 different quantum numbers. The first 3 describe the orbital itself. Remember, the orbital is the 3-dimensional space that we can find the electron. It's going to be described as a probability of finding the electron. And as soon as we determine one of these quantum numbers, the other 2 are going to depend on it. Our first one is an n, and this is the same n that we had in the Bohr, and it is called the principal quantum number. And the principal quantum number describes the size or the energy of the electron orbital. And one way to look at this is if you are in a stadium, like you're in the Verizon Center, and it's got levels. And we can describe this n value here, our principal quantum number, we can describe this as a level, or we can describe this, and one of the older fashioned ways of describing this was to call it the shell. Okay, this is a level, this is a size. And this would be like you're in the Verizon Center and you're in the 100s. You're in the first level here, closest to the ice or the court or whatever you want to look at it. The next one out would be 2 and 3 and 4. And the further out you go, the more seats you're going to get. What seat you're going to be on is going to depend in what level you're in. Level 1 has fewer seats than level 2 does. So, first one, principal quantum number or the shell. It describes the energy of this orbital, and it has values, integer values of 1, 2, 3, up to infinity. At infinity, the electron has been removed. It has been ionized. The next quantum number is going to give us the shape. So once we're in this level, so again, so imagine we're at the Verizon Center, and we're in this level, we kind of have shapes of spots where you can put seats. Well, we kind of have the same thing on the electron. We have the shape. Our second level or our second quantum number here is an L. It is called the orbital angular momentum quantum number. And L has values from 0 up to n minus 1. So what does that mean? And by the way, that is inclusive, meaning that if, say, n equals 3, we have to go to 0 and then go all the way up to n minus 1, going up by values of 1 each time. So if n is 3, then L is equal to 0, L is equal to 1, and L is equal to 2. And we have different places where we can put our electron. These are our subshells, and they fit into our shell of whatever it might be, n equals 1, equals 2, equals 3, etc. Now, because our poor little brains don't like wrapping around lists of numbers, we take and we describe our shape with a letter. So if L is 0, we always have an s orbital. If L is 1, we have a p. If L is 2, it is a d. L is 3, it is an f. And after that, they are alphabetical. We will never see those. Those are not stable in nature. They're called Rydberg states, and we're just going to pretty much ignore them. All right, let's look at a set of s orbitals. Note these all have the same shape. These are all spherical. These, we know that our L value, or our orbital angular momentum value, gives us the shape. This happens to correspond to the shape that we would get when L equals 0. When L equals 0, it is an s orbital. These are clearly not the same s orbitals. These are different sizes, which means they have different n values. This is n equals 1, n equals 2, and n equals 3. If we had n equals 4, it would be even bigger. This also is the probability. What we are looking at here is the likelihood of finding the electron in this space around the nucleus. When we are describing our orbitals, we are going to start out with the principal quantum number n. We are going to follow that by the orbital angular momentum quantum number L, and then we are going to follow that by the number of electrons. Note, this is the shell, this is the subshell, and these are going to be the 1s, the 2s, and the 3s. The distance out, n equals 1, 2, and 3, followed by the shape, which in this case is the s. This is a full set here of s, p, d, and f orbitals. An s corresponds to L equal 0, and this gives a spherical shape. Our p orbitals correspond to L equal 1. D orbitals are when L equals 2, and F orbitals are when L is equal to 3. These are the S, this is the P, this is the D, and this entire set down here are the F. Now, if we go through this, we realize we don't have the same number. If we have an S, we only have one orbital. If we have P's, we have 3 orbitals. If we have D's, we have 5. And when we have F's, we have 7 orbitals. Please note the number of orbitals. By the way, an orbital is just a space that holds a maximum of 2 electrons, is going to equal 2L plus 1. So when L is 0, 2 times 0 plus 1 is 1. When L is 1, here with our p orbitals, we are going to have 2 times 1 plus 1, and we're going to get a total of 3 orbitals. So the number of orbitals is 2L plus 1. All right, so right now we have 2 quantum numbers. We have the n value, which is our principal quantum number, which we can also describe as the shell. We have our L, which is our orbital angular momentum quantum number, which is our subshell. And then inside of our subshell, we have this magnetic quantum number, m sub L, and m sub L tells us the orientation of the orbital that this electron can exist in. Please note there are 2L plus 1 values for our magnetic quantum number, again meaning that, let's say, L is equal to 2. Remember, if L is 2, that is a set of d orbitals. And if we have a set of d orbitals, we're going to have 5 of them. Why? Because we have 2 times L, which is 2, plus 1 for a total of 5 orbitals. We are going to describe where these orbitals exist by looking at m sub L going from minus L through 0 to plus L. What does that mean? That means, again, if L is 2, we're going to have an address system. And again, this is just an address system. It's just a set of numbers trying to explain where things are. We're going to start out with our m sub L going from this value as a minus 2. And then we're going to increment that by 1 to get minus 1, 0, 1, and 2. And please note that is 5 values. And that corresponds to these 5 orbitals. What does this actually mean? This is an orientation. This tells us where they exist in space. So let's see if we can apply that on this figure right here. If we have n equals 1, we're going to have L equals 0. How do we know this? Because we know that L has values from 0 up to n minus 1. So if n is 1, the only value we can have for L is L equals 0, and this is an s orbital. Now, we also know that our m sub L, and remember that this is our shell and our subshell, our m sub L, each m sub L value gives us 1 orbital. Our m sub L goes from minus L to plus L. Well, L is 0, there's only one value, and that is m sub L is 0, which tells us that there's one orbital. And which one is it? It is this one right here. Now, what about if we have the next case on, which is when we can have n equals 2? When n equals 2, we've got more opportunities. We can have L equals 0, and we've seen that. That's the 2s. And we can have L equals 1. Well, when L is 1, it's no longer an s, it's a new orbital, and that is the p orbital. We know that the number of p orbitals is going to equal 2L plus 1, which is going to be 3. And again, which 3? These 3 right here. These are our set of p orbitals. But we have addresses to designate them. So please note that these orbitals aren't the same. This one is along the x-axis, this one is along the y, and this one here is going to be along the z. So I'll show this backwards, x, z, and y. Now, how do we know this? We know this because we can look at the m sub L values. M sub L goes from minus L, which is minus 1, add 1 to it, and get 0. Add 1 to it again, and you're going to get plus 1. And these are the values for the m sub L, which tells us which direction this is in space, of our orbitals that this electron can exist in. So what do we know? We know that when we have a p, we have 3 possible orbitals. They exist as px, py, and pz, where x, y, and z are the axes that they are against or laying on. And we can have a set of 2 p's, we can have a set of 3 p's, and this just gives them further out from the nucleus. Again, it's just an address system. Once we have this, we can sort of consider what this looks like. And again, imagine that you are in a auditorium or you're in the Verizon Center, and you can start out, and the closest to the nucleus would be this 1s. And when you get further out, you get another set of possibilities, and this is the 2s and the 2p's. And you can go further out, and you can get the 3s, the 3p's, and the 3d's, and realize that each time you go out one shell, you add one subshell. So for shell 1, when you have n equals 1, you have one subshell, and that is going to be a 1s. When n is 2, you have 2 subshells, and that's going to be 2s and 2p's. When n is 3, you're going to have 3 subshells, and you're going to have 3s, 3p, and 3d's. Now, these don't exist at exactly the same energy levels or the same distance out. So please note, if we look here at the 2, where we have 2s and the 2p, the 2s is a little lower in energy, a little closer to the nucleus than the 2p is. You even see that more when you go to these n equal 3, and you compare the 3s to the 3p and the 3d, and those are very different in energy, even such that this 4s is below that. We'll go to the details on that in a few slides. So, what are we going to use this for? Well, again, let's pretend that we're at the Verizon Center and you can sit anywhere you want. Well, you're going to want to sit closest to the nucleus, and the electron is going to do exactly the same thing. It is going to exist as close to the nucleus as possible, and it is going to be in the ground state. What is the ground state? Closest to the nucleus as possible. And we are just going to take a look and see where that is. Well, the closest to the nucleus is n equals 1. Well, when n equals 1, we know we have one subshell, and our subshell is going to be L equals 0, or the s. And what the only orbital we have, because remember that m sub L is also equal to 0, so the only orbital that we have is the 1s. Now, we need some rules. First rule is that each orbital, and remember our orbital is our m sub L value, that's -1 or -2 or whatever it might be. Each orbital, each m sub L value holds a maximum of 2 electrons. And what we're going to do when we write our address system is we're going to write the n value, then we are going to write the L, and then we are going to put the number of electrons up here as a subscript to the L. So if we have hydrogen, we have one electron. Where is it going to be? As close as it can get to the nucleus, and we're going to write 1s1. We have one electron in the closest orbital to the nucleus, and it's called the 1s. All right, we have done 3 quantum numbers. We have the n, we have the l, and we have the m sub l. But we said we have 4 total quantum numbers. Our last quantum number is n sub s, and this is the spin magnet. Now, the spin magnet quantum number describes the electron, and we are going to describe the electron as a function of its spin, and we are going to say that it has either spin up or spin down, and we describe this as a positive 1/2 or a minus 1/2, or we even describe it as an arrow, giving ourselves spin up and spin down. We're going to discover when we put electrons into the atom that in order to have 2 electrons in a nucleus, we have to have one up and one down.